Hello and welcome to the Research Matters podcast. I am your host Aarti Halpe, and in today's episode, I will be talking to Professor Arindam Ghosh and Professor Srinivas Kulkarni. Professor Srinivas Kulkarni is a George Ellery Hale Professor of Astronomy and Planetary Sciences in the California Institute of Technology, Adjunct Professor, Raman Research Institute, India, and J.R.D. Tata Chair Professor, Tata Institute of Fundamental Research, India. His research interests are cosmic explosions, gamma-ray bursts, and supernovae. He is also interested in radio astronomy instrumentation, time domain surveys, and small satellites, in addition to developing graduate-level courses for astronomy. He is the jury and the chair of the Physical Science Panel, Infosys Science Foundation. Welcome, Professor Kulkarni. It is indeed a pleasure to speak with you. Professor Arindam Ghosh is the recipient of the Infosys Prize 2020 for Physics. He is a professor in the Department of Physics, Indian Institute of Science. His research interests are experimental condensed matter physics, two-dimensional materials, electronic transport and noise in atomic membranes and nanoscale devices, and optoelectronics and spintronics with two-dimensional hybrid devices. The Infosys Prize 2020 in Physical Sciences is awarded to Professor Arindam Ghosh for his development of atomically thin two-dimensional semiconductors to build a new generation of functional electronic, thermoelectric, and optoelectronic devices. Semiconductor materials are neither good conductors of electricity nor bad conductors. The beauty of semiconductors is that we can control their electrical conductivity by adding specific impurities. This property has made it possible to make all kinds of electronic devices with it, including laptops, phones, music systems, and even the controls of our cars and household appliances. Exposure to heat or light can also change the electrical conductivity of semiconductors. Their interaction with heat is called thermoelectricity, and their interaction with light is called optoelectronics. We need to detect light for several things, from security cameras, optical fiber communications, in radiology in the medical field, or to detect signals from galaxies far, far away, that is, astronomy. Researchers have been able to make detectors that can count the quanta of light particles, called photons, falling on it. Some detectors can detect even a single photon. Professor Ghosh and his team have created single photon detectors using two-dimensional materials. Two-dimensional materials are the ones in which their molecules or atoms are arranged in a single sheet that is just one atom or molecule thick. Two-dimensional materials are said to be the most promising materials of the future. Welcome, Professor Ghosh. Heartiest congratulations. We are very pleased to speak to you today. Let us hear from Professor Ghosh why two-dimensional materials are interesting.
So basically, it turns out that these atomically thin two-dimensional materials have got some rather unique properties. They can be extremely electrically conductive, so they become an replacement for silicon electronics. And in addition, they have got extremely interesting mechanical properties. All these things started after 2004, 2005, when this class of materials got discovered. It turns out that we can also use these materials for completely new applications. For example, in photovoltaics, making solar cells, making extremely high efficiency detectors of light, of proteins, biochemical detection. So it turns out that a common material platform can do so many diverse set of tasks that it had never happened before in material science per se. So that's where the interest comes from.
Okay. And apart from graphene, are there any other two-dimensional materials which could be? I'm sure there are many, but graphene is what we have been, always hearing.
Correct. So I can tell you, Aarti, the situation now separated from bulk graphite, and then people got immediately interested and started working on it. In 2009, the second two-dimensional material, which is of major breakthrough, came, which got the molybdenum disulfide, which falls in the category of what you call the transition metal dichalcogenides. That got separated. Then immediately after that, in about a year or two, the third kind of oxide-based two-dimensional material got separated, like which is high temperature superconductors. So then it turns out that today we probably know about 30 to 40
Oh, that's
series,
nice.
the
Right.
phosphorus or something of that sort, around 30 to 40 materials which could be separated in extremely thin form. But there has been a paper recently which says that in principle there could be nearly about 2,000, nearly 2,000 of such materials that could in principle be
Oh,
separated
wow.
and made devices from. So there's a huge possibility in this area.
Okay. That's really exciting, to hear. So, what are the most interesting properties of two-dimensional materials that you are currently exploring?
Right. So, first of all, these two-dimensional materials are amazing in the sense that there are new properties, new aspects that are being discovered all over the world every day or very regularly. So our research has kind of changed over time, but initially we started with making a simple electrical transistor, like the field effect devices, which we made, and our um, from there we went into this optoelectronics where we coupled the electronic properties and their optical properties together and started working on these new structures. One of the biggest, I would say, among in India certainly the first group was ours, which combined two different two-dimensional materials in the same device,
Oh.
and that led to the same. So, for example, I gave you the example of graphene and molybdenum disulfide. What we
Mm-hmm.
did for the first time here is combined the two in the same device. Okay,
Okay.
we extracted the best of both worlds, because molybdenum disulfide can absorb light wonderfully and
Oh.
graphene can conduct electricity beautifully. So when we combined the two, it actually that's the work which was done for the first time ever. So
Oh. That's
that led to an extremely high efficiency detector of light. And once we did that, we realized that this is a gold mine, because what we can do, we
Mhm.
can create single photon detectors. And that single photon detector can actually impact quantum technologies, for example, metrology's extremely high efficiency sensing, night vision cameras, strategic
Mhm.
sectors, satellites, and so on and so forth. One of our major themes of research now is combining two-dimensional materials of different chemical genres. So, for example, molybdenum disulfide and graphene, for example,
Mhm.
molybdenum selenide, and etc., and create single photon detectors at high temperatures, because this technology does not exist today, and use it for applications. Now we are hugely emphasizing quantum technologies in particular, and I believe that this kind of ideas or devices will
Mhm.
be directly impacting the technological sectors like quantum technologies. So this is one major direction of our work, like making uh, detectors of extreme sensitivity at high temperatures using two-dimensional hybrid structures.
So, can I
And the
ask one
second part
doubt,
is more
Professor?
fundamental.
I'm sorry. Can I
Sure, please
ask
go on.
one? So
Sure,
you
sure.
mentioned high temperature here, right? So, I
Yeah,
mean, what is special about high temperature and why?
right. Yeah. So, Arti, let me tell you the current status of technology, which is prevalent for making detections of single photons in many aspects. And these are primarily based on superconducting wires or
Mhm.
superconducting single photon detectors.
Superconductors are materials that offer zero resistance to electrical charge movement. Currently, superconducting materials are possible only at very, very low temperatures, that is about minus 180 degrees Celsius. We need to use liquid nitrogen to reach such low temperature and maintain it.
When you buy single photon detectors, they're extremely expensive and non-portable. And you have a superconducting system which needs to be kept cold, and hence
Mhm.
there are a lot of peripherals that need to be considered. So
Okay.
when we decided that this could be our two-dimensional detectors are very, very sensitive compared to silicon detectors, we
Mhm.
naturally started thinking of making detectors at higher temperatures. And we actually have already demonstrated these capabilities at much higher temperature about a couple of years ago, and we are just improving their properties now, and hopefully we will come up with something similar very soon.
So high temperature here is, I mean, I'm just looking at whether high temperature is room temperature because you're comparing it to superconductivity, or high temperatures are like really high temperatures where you.
I'm talking about a room temperature operation.
Okay, okay, that's.
So apart from that, my group works on various other things because, for example, we are also trying to make thermal heat harvester using these two-dimensional materials. One of the major advantages of two-dimensional systems is that you can make these hybrid systems in any way that you want. You can decide, okay, I would like to make a thermoelectric today. You can
Mhm.
decide, okay, I would like to make electronic memory today, and so you create your materials by putting one class of material on the other and create a full device. So my group, apart from looking at the optoelectronics, also work on emulating these kind of properties through experiments on with these two-dimensional material systems.
Okay.
So that's the diversity of the work that's going on in my group.
So my next question is to Professor Kulkarni. So Professor Kulkarni, as a jury member, what do you look at while choosing an awardee?
The most fundamental thing we're looking for is to ensure that our winner uh, is in the class of our past winners or
Okay.
better.
Okay.
Okay, that is our that absolutely has to be met.
Mhm.
Uh, then moving up, we are looking for research that could be catalyzing new would lead to significant advantages in that subject or
Mhm.
in overall, so it's sort of an inflection point. Any
Mhm.
research where uh, now that the prize winner has uncovered
Mhm.
uh, some truth, it opens up new vistas or big advances.
Okay.
Um, and For our committee, we want world class work done in India. It is not necessarily has to be Indian citizens or something. It has to be work done in India at any
Mhm.
institution in India. It can be anyone or of relevance to India because some areas are outside, our prize. Physical sciences has to do with India,
Mhm.
um, and but it has to be world class.
Mhm.
And those are our criteria, and then ideally we aim to find people in some sense, and we want it to be an timely recognition.
Mhm.
So
Mhm.
the foundation has a rule that we do not want this prize to be seen as a end of your career prize. We want it to be seen as the capstone or perhaps even rising. Okay, so typically we are looking for people who are very well established and have a decade or more to go before they formally retire or otherwise.
Right.
Um, so that yeah, so this way our prize winners uh, would have a big impact because they have another decade plus to go. They could go and inspire particularly youngsters
Right.
And there's nothing wrong with prizes that are, I would say, more like the end of your career. Nobel Prizes tend to be that way.
Correct.
They're big prizes, and many people want to get them, so they tend to be end of your career. And we
Right.
are not end of a career prize for sure.
Right. So I think that that is an important prize or place to give a prize, so that a recognition at the right time will definitely accelerate probably the work that the person intends to do. I mean, I
Yeah, this
feel
way they
that's
have
right.
energy, and also the cash amount is sufficiently good that depending on where you live, you can certainly afford to buy an apartment or a small house, depending on your location, so that it makes ordinary things less burdensome.
Very
So we
true.
also want to make it not just a recognition, but of real value to our winners.
Right. Right. What are your thoughts on Professor Ghosh's work in a broader perspective? And where do you think that his contribution fits in the bigger picture?
There are two parts which very much impress the committee.
Hmm.
The first one is the work itself, which in itself has two aspects. One is elucidation of certain physical principles, in this particular case, quantum mechanics,
Hmm.
and another one is application. Um, that two-dimensional materials is a very novel area of material research, and it lies at the interface between very interesting effects in quantum mechanics, new materials, new applications.
Hmm.
And Professor Ghosh's work, for instance, um, opens up possibilities of building very inexpensive, large format photon detectors. So
Okay.
basically, like you have imaging detectors like in your cell phone,
Hmm.
um, which was a result of work done a long time ago. That starts goes back to the 70s for what are called charge coupled devices, and
Hmm.
then later CMOS, which is what's currently used in cell phones. So these sorts of new detectors, especially if they're very ultra sensitive, if they have the ability to detect single photons,
Hmm.
then the future looks extremely interesting. And we'll come later to why I personally find that interesting.
Okay.
And the second aspect of Professor Ghosh's work that definitely was impressive is that it's experimental physics work done in the Indian context.
Hmm.
Um, India has both a large number of what you might say more mathematical, more theoretical physicists, astronomers, mathematicians, and so on.
Right. Right.
And uh, part of it is, if you're not a resource rich country, in some sense, at the very least, you can sit down and think very hard with a paper and pencil. And if you're sufficiently talented, you can actually make big progress. And
Right.
that's well and good, but life is very diverse. You need to make progress on every front. You can make progress on two-dimensional material, but if you get the coronavirus, you have to make progress in biochemistry,
Right. Right.
in medicine. So, in the same way, physics is a very large area. It goes all the way from purely conceptual ideas, okay,
Right.
such as quantum mechanics and gravity, to all the way to materials, and
Right.
somewhere in between you have rockets and so on and so forth.
Right.
And for us, seeing world class research in
Mhm.
experimental physics was very heartwarming.
Right. We come back to Professor Ghosh. I mean, related to your work, can you share with us any Eureka moment that you experienced during your work, or any incident where you really had to hack your way through a difficult situation?
Yes. Okay. Uh, you know, as an experimentalist, and this is something which Professor Kulkarni did mention when he was talking about. As an experimentalist in India, I joined as an experimentalist in India in 2006, and at that point of time, making devices, and my kind of work was not there. It's as simple as that. So I would say my biggest Eureka moment was when we first created the field effect transistor using graphene, single layer graphene in my laboratory, using the existing infrastructure, and achieved a single electron, a field effect transistor with graphene in 2008. I think that was the time, and that was hugely satisfying. And that's 12 years ago, and really the group started from that point.
That's really, really. I mean, I'm sure it must have been very exciting, to do something really the first time.
Yes, indeed. In India, that was of course in India.
Right.
I mean, people have done this elsewhere many, many times, but yeah, I mean, I myself did it elsewhere in the world, but not in India.
So, Professor Kulkarni, this question comes to you. Is there any aspect of Professor Ghosh's work which you find particularly interesting in relation to your own work? Or I think you mentioned previously that there is something personally also that you like about his work. So
yes. What I like personally, I can assure you, did not play a big role in selecting Professor Ghosh. Astronomers are consumers of basically photon detectors, or in general, so for example, much of the early history of what are called as charge coupled devices, which still to date remain the best optical detectors on this planet. They have all quantum efficiency of nearly 100%. They can be manufactured in very large format, all the way across to maybe 90 by 90 millimeters, cosmetically pure, no noise, almost no noise at all. And thanks to those devices, astronomers are able to make very large and exquisite images of the sky, almost on a nightly basis. But these are expensive devices. 90 millimeter by 90 millimeter device of this quality would be many hundreds of thousands of dollars, and operating at liquid nitrogen temperature. And also mainly optical, not near infrared. So I'm hopeful. I don't know enough to say exactly which band and restrictions. Professor Go should be the one who you should ask. That with this technology, we can make very large format detectors and use that for imaging the sky at with more favorable operating circumstances, such as not going to liquid nitrogen temperature, but maybe just thermoelectrically cooled, which is acceptable. That would really, and I really hope for Professor Ghosh's sake and for India's sake that this will lead to some company commercialization of this technology into a company in India which will offer large format detectors for scientific imaging.
Yeah, taking up from what Professor Kulkarni mentioned, that eventually it would be nice if this is commercialized. Something related to that is like when people work on nano devices, I mean, like for example, even the nano transistor. So these are really, really tiny. So how does one make something which is tangible and usable? Like for anything to use, you can't use it in the nano form, right? It has to connect to outside and come out. So Professor Ghosh, what do you think? I mean, if one has to make a commercial product, then will the making process be different from the lab? And what could be the challenges there?
So, Aarti, the point here is to understand that nano itself is not a roadblock, because if you look at silicon transistors today, and their dimensions in which it works. They work in nano. I mean, there's the 15 nanometer technology that becoming now a commercial product, right? So I don't think nano itself is an issue. The issue here is bulk scale production, and really that's the only roadblock when it comes to two-dimensional systems. And because what we need to do is we need to create high quality two-dimensional uh, materials at the scale of 6-inch, 8-inch, 12-inch wafers. In case of graphene, it is already in place. In the case of molybdenum disulfide or other kind of two-dimensional materials, it's extremely advanced now. See, you have to compare silicon technology and 2D technology and give it a proper perspective. Silicon technology is now nearly 5 decades old, 50 years.
Right.
And the material discovery, the optimization, and the foundries that you see has happened over the years. Two-dimensional technology, the material per se is just about a decade old, or probably less than that, right? So what Europe and many other places are now completely focusing on is creating large quantity of these materials, a large area of these materials. And if that happens, then it's just a question of standard foundries that what they do to make such devices. So I'm quite certain that it's just about the material quantity challenge that is waiting for commercialization. As far as this work, our work is concerned, we have already got the patent of this work, and we believe that we should be able to take it forward further and see where it takes us, really.
So here, so for example, the size of the devices that you make right now, I mean, I have no perspective on the actual size, but I'm imagining that is probably much, much smaller than what would be commercially required. Like you said, a large wafer, if you compare to silicon, like the device is small, but the wafer is large and that kind of a thing. So would there be, challenges different from your direct area of work to get that done? Like,
so there are always going to be engineering challenges, but at the same time, I do not see a fundamental difference between a camera, which works as like a CCD camera or whatever it is, an imaging device with a multiple pixels, which collect photons and converts to electricity. But in terms of the simple size parameters, there is not much difference at all with the existing imaging techniques. In addition, of course, we have ability to the band which Professor Kulkarni was talking about, which band of operation is extremely flexible. You just have to choose the right material to hit the band of wavelength that you would like to investigate or explore for either astronomical purposes or anything else.
These questions are actually addressed to both Professor Ghosh and Professor Kulkarni. Once scientists discover new useful materials and their properties, what happens next? So what is the kind of flow? How does this knowledge get used for creating objects or helps practical problems? And typically, how long does it take from, say, a discovery of a material to a prototype to a commercial product? So I mean, it's just trying to understand the flow of what happens after a discovery.
Okay, right. So, Aarti, it depends very much on the field. Okay, so I don't think there is an obvious answer to the time scales from the discovery to the final commercialization or a final product that comes to household or gets applied. I can tell you the steps here. First of all, when a phenomenon get discovered, you need to understand the mechanism behind the process. What is happening? Why is it happening? And then you start looking at possible improvisation or improvement in the process. And then that takes a bit of time because you still are trying to perfect the discovery. But you know that the phenomenon is there, right? So there's a bit of incremental engineering aspects associated with it. And then in the process, you also find out what are the possible applications. See, when a discovery happens, it doesn't come because of an application. A discovery happens by itself. And then you start looking at possible discoveries. And even in this case, it was the case. We were just having fun with some two different materials, putting them together. And then we found that this amazing ability for them to convert light into electricity. After that, it comes out to be material challenges. So then you look at the problem that I just talked to you about. That, okay, how can I make a large enough quantity of it so that it can be commercially meaningful, or even for certain applications. For example, if you want a large detector for astronomical purposes, you need to really create a large area of these materials. And finally, actually proper payload tests or on-field trials, which first of all, you need to create materials, and then you need to engineer devices, and then you have to scale up those devices, the quantity as well as quality. And finally, you need to do reliability checks and many other processes. So it depends on very much on the time. The discovery we are talking about is just about 5 years old.
Okay.
So probably one would say in another 3 to 5 years, this one probably will be in a position where people should be thinking very seriously on its application. And hope this, of course, but I mean the condition that we will have a proper large-scale material growth in place by then, because the rest of it is more or less ready.
Right.
Yeah.
Professor Kulkarni, you would like to comment on this topic?
I really am not much into the, it's not my area. So I don't think I can add anything of, of great value.
Okay.
Other than hoping that this will lead to a very, specialized small company that will start making these.
Yeah. So now this is a sort of general question. So while creating solutions for practical problems, so some very basic could be like treating industrial effluents to make them harmless, or making wearable electronic devices. How do science and scientists and engineers and engineering play a role? So what are your thoughts on that?
Let me tell you, at Indian Institute of Science, this is one of the major directions that we are, or major initiatives that we are exploring, that how to take a scientific discovery or a scientific result or research output, and then allow engineers to get engaged, and then take that to a commercially or economically and from consumer points of view, a viable product. So it's usually it starts from a scientific result, and the engineers then come in to make the scalability aspects of it. Most of the scientific discoveries are at a single modular level, but that's not really something very useful. What needs to be done is to see, if you make millions of them, whether A, that is possible, and B, whether that retains its functionality as the original module. So that's where engineering comes into play in a very big way. And what we are very fortunate of, in this institution at least, and I'm sure it's in some of the most successful places in the world, where we have a synergy. We have a synergy between scientists and engineers, and we have engineers who are actually directly working in two-dimensional fields, which is the context in this case, and willing and ready to take this further forward in to make and to check if there are devices that could be made, a multipixel camera, for example, in this case, or even if you forget about this device of ours, if you take a look at graphene as a electronic component or electronic product, there are engineers now who are looking at a 1 million transistor or 10 million transistors on a wafer made of graphene for applications which could be optical modulators or whatever it is. Okay. So that's where it is now. It's a new field. It's about, as I said, about decade and a half old field, We have to give it a little bit more time, but I think consumer products are now coming out in various parts, and it will come out in a large number of different areas, I believe.
So I mean, even talking about graphene, I mean, a thought that occurs to me is that suppose graphene were to use in a wearable electronics, somebody would have to check, right? If you bend the graphene layer, is it possible to do it, or what happens if you bend it, or
Yeah,
so
so
that
this has been done.
okay.
These kind of research has already been done. There have been graphene put on flexible substrates called PDMS and other kind of
Mm-hmm.
materials, and the ability of graphene under bending has been demonstrated now reasonably long time ago. I mean,
Mm-hmm.
in the context of
Yes.
graphene, 1 year back is a long time ago. Really. I mean,
Okay. Right.
it's that fast a field.
So that engineering
Yeah.
does engineering. I mean, is engineering involved in that? Like how much you can bend, or when you design
Yeah,
something, what
yeah, of
what is the
course.
curvature, or
Yeah. So that's why the flexible substrates, actually, even not just graphene, or many other two-dimensional materials have been put on flexible substrates, and their physical, optical, electronic properties have all been tested.
Mhm.
As I said, the basic workhorse is ready, and
Mhm.
one of the huge surprise, I wouldn't say surprise, but impressive factor of graphene is its ability to bend and recover its own shape afterwards. For example,
Okay.
if you take a standard silicon or standard material or a metal, if you
Mhm.
bend it more than say 0.4, 0.5%, it's you do not you do not get back the original shape. It sort of becomes distorted permanently.
Right.
Whereas if you take graphene, you can bend it by nearly 5%, 10 times more than that, and you will
Mhm.
still recover its shape and structure. So this is a unique aspect of these two-dimensional
Mhm.
materials. So this is why people are so excited by it.
Right. So, Professor Kulkarni, I would like your to hear your comments also with the science and engineering aspect of any work or any application.
Well, I'm a firm believer that science without technology to me makes no sense at all. I know it sounds like a strong
Okay.
statement,
Right.
uh, but in the business I've been in, which is a phenomenological science, astronomy is discovering the universe as it is. Just like biology and geology, they're all phenomenological. It is the biology is about certain low energy complex reactions that produce rather amazing materials, which then can even get life and so on. And geology is a rather complex phenomena of metals and rocks and so on and so forth. I honestly think there is no such thing as a pure thought science. And in fact, I would say this has been the curse suffered by particularly the Asian countries and or in general in the Asian countries and in particular India, that we tend to think thought matters a lot. I don't think so at all, actually. I think the progress in science is directly a function of technology. We have been misled by historical analogies like Newton is sitting under the tree and an apple
Right.
fell on his head.
Yes.
It's a misleading statement because many apples have fallen on many people's heads before.
Right.
Okay, and that didn't lead to the theory of gravity. Newton was a very rich person, very well educated, and England was its close to it. That invented the steam engine. It was a
Right. Right.
leading economy in the world, and he was at the leading one of the leading institutions. So he had, in some sense, the access to technology of a sort we may not immediately understand.
Mhm.
And then the next example people give is Einstein. They'll say, "Oh well, he's just sitting in the patent office." No. In fact, there's a lot of data on the speed of light and how it doesn't change with with
Mhm.
the Earth's orbit. There's only so much progress you can make by pure thought.
Mhm.
Maybe bits, bent pieces in number theory, but maybe even that has come to an end. Maybe there'll soon be a mathematics which involves machine learning for
Mhm.
proofs and so on. To make it short, I think science without technology is very stifling, and technology without science doesn't really lead to dramatic advances. It leads to gradual small improvements,
Mm-hmm.
but never to big changes.
Right.
And so these two go together.
Right. Right. Yeah, that is very true. I mean, I think doing something and checking is an important aspect. I think
No, no, not so important. It is
it is.
science.
Yeah. Right. That is
You
true.
know, the big difference between science and religion is in religion you assert,
Right.
and your assertion is so strong that you dare not check.
Right.
And as I said, that's why for us a prize of this sort, recognizing someone who's doing experimental physics, inventing new things, verifying quantum mechanics in novel situations, we couldn't think of a better prize winner.
Right. Right.
And I hope your podcast reaches to some young people who will not be mesmerized by mathematical elegance and proofs and so on, because I think we had too many theorists in India,
Right.
and it's we have reached the end of that road long time ago.
I don't know. I mean, is it to do something with the availability of resources in addition to the glamour of theoretical
Well,
view?
I might want to add to that what
Yeah.
Professor Kulkarni just said, and actually you correctly pointed out.
Right.
See, there had been a lot of time, particularly mid '80s, mid '90s, and so on and so forth, where really the resources for doing experiments in India was extremely poor, and you could come back to India and do bits and pieces, this and that, and really not come to the global standards.
Right.
Whereas there are high quality theorists who came to
Mhm.
India at that time because for them that resource crunch was not a major issue. Of course, even at the personal level, salaries and so on and so forth were not great at that point of time. But still, at least you could do work. You could work
Right.
at your and keep in at the cutting edge. Whereas if you look at the mid 2000 onwards, that's roughly when I joined.
Right.
There's a series of new young faculty joined at that time
Right.
who are now working on difficult experiments, and it gives me enormous amount of optimism, to be honest, that
Right.
we are actually now developing a very high quality experimental infrastructure, which should produce the first time in the world. I mean, I always tell this: we have to do something for the first time, and we
Right.
should be able to do this more and more often in the coming years.
So both of you have mentioned this in our this discussion, but as any concluding remarks on what do two-dimensional materials have for us in the future? So I guess both of you have touched upon this, but like I said, a concluding remark on this.
Two-dimensional materials is a new kid in the block. One has to understand that. And there are a large number of possible applications which can be disruptive technologies. For example, silicon electronics becoming replaced by molybdenum disulfide or TMDC electronics because of uh, several advantages. And also there are new functionalities which is simply not possible with existing technologies. Now which one will come first is still to be seen. There are now companies which have invested in making 2D systems in composites, which are now already commercial products. There are companies, large number of companies in the composites for rubbers, composite for steel, composites for lightweight alloys, which can be used in airplanes and so on and so forth. And they are now becoming more and more, commercializable in the next few years. I can see the hardware applications, for example, electronics, in its present form might take a little more time, but niche applications like optoelectronics, like memories, are another. So they probably will uh, become more attractive uh, at earlier time scale because there are no existing solutions for such applications. So
Okay.
I think the future of this is becoming more and more. I'm going to be cautious. cautiously optimistic about it. But if and when the material challenges are addressed, this is probably one of the most important technologies that we have developed in the last decade or two.
It's very hard to predict, especially the future.
Right.
Okay. So there are many neat discoveries or findings, and which of them takes off is a complicated question. It has to, there's always a timeliness for any new discovery and new technology. But in a sense, from all the materials in electronics we have used have been three-dimensional structures, and there's no question we've mastered that. Transistors have gotten smaller and smaller, and there's always been a concern: how can we keep at it?
Okay.
And we have reached some limits there. So in that sense, a paradigm shift is always welcome. And the question is two-dimensional structures the correct one?
Right.
It looks very promising. For example, let's talk of something as simple as take a graphene ribbon. Graphene turns out to be an excellent conductor. Okay, so if you want to conduct a large amount of electricity, like in power stations, and of course, Professor Ghosh has to correct my general statements. It looks very promising. Now, I don't know what are the practical difficulties, but in the lab, it does look like graphene ribbons are far more attractive compared to, like, say, copper wires, which, are the mainstay of, I'm talking really heavy electrical currents in power stations.
Right.
And if this works out, for example, let's say, there are always some practical issues. If this works out, just imagine the convenience. First of all, copper, you have to dig around, it's mining, it's all sorts of things. And maybe the mines are getting harder and harder to find. There's plenty of graphene, there's plenty of carbon. In fact, we have a lot of that in our atmosphere. And if we can, and it turns out to be, let's say, very highly conducting, so the losses in the sheets are much smaller than in copper wires, that will be a fantastic thing. So I would say, there's a good grounds for optimism that this two-dimensional, the era of two-dimensional electronics may be just around the corner.
In fact, I just want to add what Professor Kulkarni said. I mean, of course, ribbons of graphene is one aspect, but even if you can make a graphene with proper boundaries, I mean, there are now work, and we ourselves did some work on that. You actually can make current flow without any resistance at all along the edges of these graphene structures. So, and that's one of the major, and those are at room temperature. You don't see even at room temperature. They're not superconductors, but they will flow along the edge without suffering from any collisions. The electrons can move as quickly as freely as they can. So that's conduct. Yeah.
That means there will not be heat dissipation also if there's no resistance.
That is correct. That's right. So that's one of the major directions in which people have now started working on in the last few years. Is topological aspects, and graphene, as well as other two-dimensional systems, several others, which has this property where you can actually make certain edges of these, or the boundaries of these materials, completely free of electrical resistance.
Wow. So before we conclude, do any of you want to say anything, as in, any message or for the listeners, or for maybe the young people who would listen?
Well, I already given my sermon, so I'll leave to Professor.
Okay, maybe I can add, because Professor Polkari, actually, during the award ceremony, Dr. Krishna, he mentioned that I'm the first experimental condensed matter physicist who has been awarded this highly prestigious prize, and I'm, of course, myself grateful and honored. But what I feel is that I represent a very large, aspiring set of scientists in India who are very young, because obviously, as you see, that they have joined much later. I mean, maybe less than a decade or so.
Mhm.
And they are working very hard, and they have to work 3 times harder, probably, than many other established fields in India. And what I feel is this would be a major boost to their morale. And I think they are becoming more and more ambitious, more and more aggressive in pursuing science and doing
Mhm.
experiments in India. So I just hope that this trend continues and people find purpose. It's not just the award, but it's just also because of simply being at the forefront of global
Right,
experimental
right,
research that should be heavily, you know, appreciated.
right, right. Yeah, I think this award in that sense definitely boosts their you know mm, motivation, morale, and yeah, let's hope we have more experimental work going on here. That is really a cutting edge. Thanks a lot for your time, and thank you very much for speaking with us today. Thank you for listening to this episode of Research Matters podcast. For more such science news and podcasts, please log on to www.researchmatters.in.